Welcome. This is our first video in our series on the mathematics of apportionment. And we're going to loosely follow chapter 4. And the main goals are going to be to realize there are multiple ways to apportion indivisible objects to different parties. And what we mean by this is what we mean by the indivisible objects, and the apportion part is we have objects that can't be broken into pieces, and we need to share them amongst some parties. And so we're going to present multiple ways to do that, and we're going to kind of conclude that there's not really a best method on how to do that division. So this first video is going to be just about setting it up. We're going to show a problem that highlights the apportionment issue, and we won't necessarily resolve it, but we'll get an idea of where we need to go. So, apportionment is often brought up in the context of a government and the seats in a representative branch of government, and how they're going to be distributed amongst the different bodies of power. So usually like a state. So our first example here is we're imagining that we have a country with 4 states. There's 200 seats in the House of Representatives, or whatever the representative branch of government is called. And we have this table, and the table tells us how the population of the country is divided amongst the states. And so the question is, well, you have these 200 seats. How do you give each of the 4 states some seats? And that's the apportionment problem. What do you do? And so there's one kind of straightforward way is equal distribution, where, there's 200 seats and 4 states, so why not just give every state 50? And somehow this probably contradicts your sense of fair. There's this sense that, well, state A is much larger than state C, so it should probably have more seats in the representative branch of government. So your next inclination might be, well, why not make them proportional? Let's try making them proportional. The distribution of seats, or the apportionment of seats, we should use the right word, proportional to each state's population. Alright, so how do we do that? Well, in that case, we need the total population. So we should add up all those populations. Here we are. 4360 plus 2280. I'm just leaving off those extra 3 zeros because they're on all of the numbers that we're adding up, so it's fine. We can just kind of toss them in at the end. So that 10,000 will have an extra 3 zeros. So 43,600, bing, ding, ding, plus 2280, dun, 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 plus 7, 2631,000 equals 10,000. Okay, well, that's a nice simple number to work with. Then A should get, and we'll just kind of see the percent of the total that A represents. I think there's one more zero there. And you might see this one all these zeros cross out, and that's 436 divided by 1,000. I'll write that, but then hopefully we'll see that that's 436 thousandths, or 43.6%. So A should get 43.6% of the seats. That means 0.436 times the total number of seats, which is 200. I'll bring our calculator back for that. It's 87.2. Okay? And so we can follow the similar pattern for B, C, and D. Note, though, that since we had such a kind of simple total population, that the calculations of the percentages is relatively simple. The 43.6%, you can just kind of read off from the front of the A. So there's 4,360,000, and then the 43.6%. Those are the same because the total population was a power of 10. So we can also use that line of thinking to say B should get 22.8%, or 0.228 times 200, 0.228 times 200, 45.6. C should get, that'll be 7.29%, or 0.0729 times 200, 0.0729 times 200, 14.58. And then finally, D should get 26.31%, or 0.2631 times 200. 0.2631 times 200. 52.62. So now we have a different apportionment, and here let's copy this down. Say copy. And then we'll add our kind of equal, and then this will be proportional. So we'll have 87.2 for A, 45.6 for B, 14.58 for C, and 52.62. And all that is great, except we can't distribute any fractional part of a seat. These are seats in a representative branch of government. These are how many people will represent state A, B, C, or D. And you can't be represented by 87.2 people. This is the indivisible part of the objects that we're distributing. So you might say, okay, well, let's just round it. What if we round? What if we round using standard rounding rules? What about standard rounding? Let's see. Let's call it conventional rounding. That's a better phrase. Conventional rounding. And then, so 87 will round to, 87.2 rounds to 87. 45.6 will round to 46. 14.58 rounds up to 15. 52.62 rounds also up to 53. And there, okay, now we have a whole number of seats given to each state. Everything seems all hunky-dory. We just need to check one thing, which is how many seats did we actually apportion? 46 plus 15 plus 53. And see, herein lies the problem. We distributed 201 seats. We apportioned 201 seats, but only had 200 to give out. And this is the crux of the problem. Conventional rounding just doesn't always solve your problem. Sometimes it will, but in this case it doesn't. And so, in general, we need a method to go forward. If you just have a finite amount of objects to pass out, in this case seats in a representative branch of government, you need a method to distribute them so that you end up with whole numbers and you use exactly as many seats as you had. So this is the apportionment problem. There's a couple kind of vocabulary pieces going on here. These are often called quota. The seats that are given out are often called quotas, with the proportional one being called the standard quota. You have the populations, and even if you're not necessarily talking about populations of states, we might often use that word to discuss the relative sizes of the recipients of the objects. And so in this case it was states, but it could be towns or counties or some other kind of body that has relative sizes given by a population or some other number. And that's it. That's how these problems go. Or in the next videos, we will discuss actual methods for solving these apportionment problems. I'll see you there.